Hello everyone. Now let us talk about Gauss Quadrature, also sometimes known as Gauss Legendre Quadrature. Okay, so let us say that this is your x-axis and this is some function fx. So when you say integral of from a to b fx dx, so we have all seen in all previous lectures that when you say integral of fx dx, you are interested in finding out the area under this curve. Okay. But when we were discussing about trapezoidal method, what we did is we replace a complex function by a simple polynomial of first order. Okay, that is a line. A first order polynomial is nothing but a line. Okay, so this is what we did in trapezoidal rule. Also in Simpson rule, the only thing we did was we replaced this line by a second order polynomial and third order polynomial and so on. So one thing you might have noticed at this point is that in all the methods that we have discussed, we have always kept these endpoints at fixed. These endpoints as fixed. Okay, so when you talk about Newton-Coase methods, we kept these endpoints as fixed. Okay, what if we had a freedom of not fixing or placing these points as per our wish? Okay, then I think a lot of good things can be achieved. So basically in Gauss Quadrature, what we do is we have a freedom of placing these endpoints wherever we want, such that the value of the integral that we'll be getting by this is going to be same as that of the analytical method. Okay, so in Gauss Quadrature, what we do is we have a freedom of placing these points. Okay, this is just 2 points. Okay, there can be a number of points, so we have a freedom of placing these points anywhere we want, such that it compensates. Like let us say we place this point. Okay, let us say we place this point. Let me use a different colored pen. We place this point here. Okay, and we place this point here. Okay, and this is A, this is B, this is B. Okay, and this is FA and this is FB. So if we place this point here, the area under this curve is going to be equal to the area under the actual curve. Okay, so basically what is happening, some error, if you see here, it's getting some error is getting added and some error is getting subtracted, and basically what we are trying to do is we are trying to balance. Okay, we have 2 points and we are trying to balance such that we get the value that is close to the analytical value. Okay, so basically what we do is, if this is my function, I take one function, I take another function, okay, and I try to balance it with weights. Let us say this is weight W1, this is weight W2. Addition of some value of A, function of A, subtraction of some value of A, and we try to balance it. Not only FA and FB, there can be a lot of other points. Let us say FC, FD, and the weights is going to be W3, W4, and the list continues. Okay. So this is the concept of Gauss Quadrature. Okay, that is why if you see, Gauss Quadrature is also known as open method, because the endpoints are not fixed. We have a choice of placing the endpoints where we want as per our choice. Okay, so this was just an explanation, but when we talk about the actual formula of Gauss Quadrature, the actual formula is, let me use a white colored pen. The actual formula is integral of -1 fx dx is equal to c0 fx1 x0, sorry, c1 fx1, c2 fx2, and so on. Okay, it's up to you how many points you select. Okay, but when you select just these 2 points, this is known as Gauss. This is known as, let me remove this Gauss because we are already discussing Gauss Quadrature, so it's understood. So this is known as 2-point formula or 2-point Gauss Quadrature formula, when you just include these two constants. Okay, and when we include these three weighing functions and functions, this is known as 3-point Gauss Quadrature formula. And similarly, if we add more points, it's going to be 4-point Gauss Quadrature formula, 5-point Gauss Quadrature formula, and 6-point Gauss Quadrature formula. Okay, and the values of those formulas is here. Okay, I'm sorry. Okay, let me bring this here so that I don't know how to bring it here. Anyways, we will just discuss it here. So these are my weighing functions, weight functions or weight factors, and these are my functions, actual functions. So when you take 2 points, so these will be the values. So these are the ready-made values that you have to take. Okay, when it is 3 point, this is what the weighing function you are going to take, and this is going to be your function arguments. When it is 4 point, this is what is going to be. Okay, and then it's going to be 5, 6, and so on. Okay, as you increase number of points, the percentage of error goes on decreasing. Okay, we'll see with an example how that happens. Okay, so this is Gauss Quadrature. So to understand this better, let us solve one simple problem. Okay, and to keep things simple, what we are going to do is we are going to take, let me erase this. We are going to take the same formula, the same problem that we did for the trapezoidal method. Okay, so that we will be in a condition to compare both these methods. So I hope you guys have understood what I'm trying to say. Okay, so let us write down. Let us write down the problem. The problem is for x cubed okay, so this is the integral, and the analytical value of this integral was 1104, if you guys can remember, 1104. So we have to solve this problem using, let us say, 2-point Gauss Quadrature. Okay, so when you say 2 point, we are just going to use 2 weighing functions. When it is 3 point, 3 weighing functions, and so on. Okay, let us solve this by 2-point Gauss Quadrature, and later we'll also solve it by 3-point Gauss Quadrature, and we'll see what happens to the error. Okay, now one thing you might have noticed that the formula of Gauss Quadrature here, this is the formula of Gauss Quadrature, and you might have noticed that the limit of this formula starts from -1 and 1. Okay, so to be able to apply Gauss Quadrature formula, we have to convert these given units, that is in this problem -2 and 4, to -1 and 1. Okay, now to do that, you don't have to worry, you just have to remember a simple problem. So any problem you encounter for Gauss Quadrature, you're just going to follow this formula. You're just going to follow this formula. So let me write down this as step number 1. So what is step number 1? That convert. So this is for any problem that you're going to solve by Gauss Quadrature. If it is a problem of double integral, triple integral, whatever it may be, the first thing is you are going to convert the limits of integral to -1 and 1. Okay, now for doing that, you just have to remember this formula, that is x is equal to b plus a divided by 2 plus b minus a divided by 2 into xt. Okay, so what is b and what is a? This is going to be your a and this limit is going to be your b. So if you do that, your x is going to be what it is going to be. If you substitute, this is going to be 4 minus 2 plus 4 plus 2. This is going to be 2. This is going to be 2. This is going to be xt, and that comes out to be x is equal to 1 plus 3 xt. Okay, so now let us replace this limits from -1 to 1. Okay, to do that, what we'll have to do is we'll have to substitute the value of x in this equation and get the value of xt. So let us say xt. Okay, when the value of x is -2, so when you substitute -2, this is going to be -2. When 1 comes on this side, -3. -2 minus 3 comes out to be -3 divided by 3 comes out to be minus of 1. Okay, and let us say this is 4. So this is going to be 4 minus of 1, 3. 3 by 3 comes out to be 1. So you can see how by using just this formula you are able to convert the units into -1 and 1. Okay, so I just wanted to show you, but next time when you solve this problem, you don't need to check whether the limits are getting converted into -1 and 1, provided you have applied the formula correctly. Okay, you have applied this formula correctly. But it is always a good habit to check the limits. Okay, and then you'll understand what mistake you have done. So basically what I have done is I have converted the integral, from the limit of -1 to 1. If you are going to replace x in terms of xd, you also have to replace dx. So if you derive this equation, this comes out to be 3 into dxt. Okay, so basically if I'm going to write down the integral, it says -1 1. This is going to be, let me first write down the, okay, let us just so what I have done is I have converted this integral into this, that is -1 1. In place of x, I'll replace it by 1 plus 3 xt. Let me use this bracket. Okay, minus of 4 into 1 plus 3 xt, this is going to be cube, plus 2 raised to 5. Okay, we forgot one more thing. We have to replace dx by dxt, and also there will be 3, so let me bring this 3 here and dx. So this will be our converted integral. So this integral we have to solve. Okay, so this will be the actual integral that we are going to solve now, which is equal to, since we are using 2-point Gauss quadrature, okay, understand one thing, this whole thing is f of x. Okay, so not, this is not f of x, no, this is not f of x, this is f of x. Okay, so this is going to be 2-point, so there will be 2 weighing functions. So this is d, so this is x d0 plus c1 . So according to 2-point Gauss quadrature, what are the weighing functions that I am going to use? The weighing function is going to be c0 and c1 is going to be 1, and this x d0 is going to be this. Okay, so basically x0, that is nothing but x d0 is minus of 0.57735. I'll have to truncate it somewhere. Okay, I'm just using 1, 2, 3, 4, 5 decimals, and x1 is going to be x d1 in our case, that is plus of 0.57735, which is nothing but I think 1 by root 3. If you guys can just check it. And c0 and c1, so c0 is 1 and c1 is 1. Okay, so what we are going to do here is we are going to replace c0 by 1, c1 by 1. Now what you have to do is we have to calculate fx d0, fx d1, and how we are going to get that? By substituting this x0 in this equation and this x0 again in this equation, in the same equation. Okay, so once you do that, if you substitute the values, you will find out that the value of I'm not going to do it, you guys can just substitute the value and just get the values, and you will find out that the value of fx0, fx d0 in our case, is 8.6424, and fx d1 is 66335. Okay, and now when you substitute these values here, that is 8.6424 and 6635. So the value of integral comes out to be how much? It comes out to be 671.92, which is way off than our analytical value. So what is our analytical value? 1104. If you want, you can calculate the percentage error. It comes out to be 39.13%, which is not good, but still better than the trapezoidal method and Simpson 1/3 rule. Okay, so now what we are going to do here, so this is how we have to solve it. Now the next thing what I'm going to do is I'm going to solve it using 3-point Gauss Quadrature. Okay, so basically what I'll have to do is I'll be using this weighing function, this weighing function, and this weighing function. Okay, let me just see if I have a space here, or else I'll have to use okay, I think I have to use different page. Let's move on to the next page. Yes. So let us solve it by three-point Gauss Quadrature. Okay, so somehow I am successful in writing down the whole thing. So again, this whole thing, always remember, the whole thing is going to be your f of x. Okay, so since we are using 3-point Gauss Quadrature, this is going to be c0 fx0. Okay, in our case, let us be consistent. xd0, c1 fx d1, c2 fx d2. Okay, now what should the value of c0, c1 and c2, and what should be the value of xd0, xd1 and xd2? So you don't have to worry. Whenever you'll be given this problem, you'll always be given the table. This table will always be given to you. Okay, so you just have to take these values, this value, this value, this value, this value, this value, and this value. It's always going to be the same. Immaterial of whichever problem you're solving, it's always going to be the same. So what is the value of c0? Guys, 0.555556. I'll have to truncate it somewhere. So what is the value of c1? 0.88886. Okay, and then c2 is 0.555556. Similarly, what is the value of x0? Minus of 0.77459. Okay, then xd1 is going to be 0. That's nice. That is going to simplify the whole calculation. And xd2 is going to be 0.77459. Okay, so when you substitute this value in this function, okay, and this value in this function and this value in this function, you'll get the value of xd0 as 10.4179, the value of xd1 is going to be -6, and the value of xd2 is going to be 1986.31. so this is going to be 0.55, just substitute the values, 5556, this is going to be 10.4179, this is going to be 0.88886, this is going to be -6, this is going to be 0.555556, and this is going to be 1986.31. so when you do the whole calculation, the value of integral comes out to be 1103.96. Wow, which is very, 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 very close to the analytical value, which is 1104. So you'll realize the percentage error that we got here is 0.003%, which is a great thing. Okay, so this is your 3-point Gauss Quadrature. Okay, and if you're curious, you can do 4-point and 5-point. I'm pretty sure after 5 or 4-point you won't be able to do 5-point because it becomes very math intensive. So basically we solve this using computer programs. Okay, and if you're curious enough, you can develop your own MATLAB program to solve this. Okay, so I think this will be all for now. Thank you.